And with the lesson on absolute value functions, our unit is coming to a close. We will consider a function of the form f of x equals the absolute value of ax plus b. So the absolute value that we're considering is a linear expression. And this type of function is the one that we're going to be studying. We're going to look at how to sketch it and its features. Of course, the parent function of this type is f of x equals the absolute value of x, where a is 1 and b is 0. And let's begin by considering how we can plot this function. What we have is f of x is equal to the absolute value of x. Let's create a table of values for x and for f of x. Let's say we're going to start at x is negative 2, negative 1, 0, 1, and 2. You know what the absolute value does. So the absolute value of negative 2 is simply 2. The absolute value of negative 1 is 1. And then it's obvious that those values are 0, 1, and 2. So let's plot. This is our x-axis, and this is our y-axis. So when x is negative 2, y is 2. So we have a point here. When x is negative 1, y is 1. So we have a point here. 0, 0 is the origin. Then when x is 1, y is 1 as well. And when x is 2, y is 2. Now this looks interesting because if you look at it, those 3 points seem to be on a straight line, and those 3 points also seem to be on a straight line. So what we have is this kind of curve. And if you look at it, it's a V-shaped curve, and this is a characteristic of the absolute value functions of this type. The vertex is at the origin, and it's important to note that the domain is such that x belongs to the set of real numbers, but the range is such that y is greater than or equal to 0. Now, if you consider this graph again, and you look at it, you will notice that this line represents y equals x. And for this part of the curve at least, the two curves match. Y equals x overlaps this part of the graph of f of x equals the absolute value of x. But then this part of the curve of the line of y equals x is allowed to be here because x can take negative values. But when you're considering the absolute value, the negative values are not allowed. So those values are reflected in the y-axis such that this point goes to this point, to its absolute value. At negative 1, it goes to 1. And this point, which was at y equals negative 2, is reflected to this part at 2. So you can also obtain the graph of f of x equals the absolute value of x by simply sketching the line y equals x and reflecting any part of that line that lies below the x-axis, and that part can be reflected in the x-axis. We can also consider something else. if you consider that this function comes in two parts, this part looks like y equals x, of course, but this part looks like part of a graph of y equals negative x. So we can redefine f of x as a piecewise function. We can say that for this part, f of x equals negative x for the values of x that are less than 0, and it equals x for the values of x that are greater than or equal to 0. Now, why did we choose the equal to be here and not here? It's a human decision. We put the 0 with the positive part, but that's not absolutely necessary. It's a matter of convention. Let's consider another example. F of x is equal to the absolute value of x minus 2. Let me just do this first. Okay. We can start by sketching the line y equals x minus 2. And as you know, this has an intercept of negative 2 and a slope of 1. So this line looks like so. This is negative 2, and this is 2, and this is y equals x minus 2. And of course, it continues that way. Now, if you look at this line, this part lies below the x-axis. That means that the function takes negative values here. Those are not allowed in the absolute value function. So what we do is that we reflect this part in the x-axis. So let's just tidy things up. This is x, this is y, this is 2. And if we want to sketch y equals the absolute value of x minus 2, it simply follows the same part of this curve because it's in the positive, but this part is reflected in the x-axis. An easy way to do it is to look at the intercept. The intercept is negative 2, so the reflection will be at 2, and an easy way to do it is just this, and this would be your curve. The characteristic V-shaped as well, but this time the vertex is at x equals 2, which is the value of x that makes this expression a 0. 2 minus 2 is a 0. Now let's try to redefine this function as a piecewise function. F of x is equal to, and here's our curly bracket. This part is exactly the same as y equals x minus 2. So it equals x minus 2 for the values of 2 or more. And this part, well, you don't have to think much about it. Simply change the signs of what's inside the absolute value. It's negative x plus 2 for values of x that are less than 2. And there you have it. So we sketched the function and we redefined it. Let's do another case. Let's say that we want to do 2x plus 6 in the absolute value. The intercept is 6. So let's say 1, 2, 3, 4, 5, 6. The intercept is 6 and the slope is 2. So we will pass through this point, and let's begin by considering y equals 2x plus 6 as a straight line without absolute value. In this case, we'd go down to here, and our line will simply be like so. Let's improve that. The x-intercept is obviously -3, which is the value of x that makes this expression a 0. Now, this is y equals 2x plus 6. Now, for our absolute value function, this part is not allowed because the y values are negative. So we simply reflect. This part remains the same, but this part is reflected. In the x-axis. So this would be f of x is equal to the absolute value of 2x plus 6. Again, the characteristic V shape is apparent. The vertex is at x equals -3. However, the line does seem steeper on both sides because the steepness of 2x plus 6 is 2. Now, let's redefine f of x as a piecewise function. F of x is equal to, we have 2x plus 6 for the values of x greater than or equal to -3. And for this part, simply change the signs. -2x minus 6 for values of x that are less than 3. Let's sketch this very quickly without having to worry about squares, and let's redefine it. I know that the vertex will be at 2x minus 5 equals 0. And that gives me that x equals 2.5. So I can quickly sketch and my vertex is at 2.5. Let's say this is 2.5. It's going to be a V-shaped, and when x is 0, the absolute value of -5 is 5, so it's going to be here, more or less. Actually, let's do it better. It's going to be double this distance, so it's going to be somewhere here. And then, simply, your V-shape. And that's it. And if you want to redefine it, f of x is equal to 2x minus 5 for values of x that are greater than or equal to 2.5, and change the signs, -2x plus 5 for values of x that are less than 2.5. Now, you should be able to, first of all, sketch an absolute value function of the form f of x equals the absolute value of a linear, and you should be able to redefine an absolute value function as a piecewise function without the use of the absolute value signs. And having done that, let's take things one step further, just for a quick challenge. If this is the curve of y equals f of x, obviously it is not linear. Can you sketch y? Can you sketch y equals the absolute value of f of x? Think about that for a while. Well, we don't know the equation of the function. We don't know the expression that gives us f, and we don't really care. We have the function. Absolute value of f of x means that y cannot take negative values. So we have a problem from here to here because all those values are negative. We do not have a problem here because f of x is positive, and in that case the absolute value of f of x will be exactly the same as f of x itself. But for this part, which is taking negative values of y, it will be reflected. And to do a reflection accurately, take two interesting points. The y-intercept is close to -4, so the reflection will be close to 4. The vertex here is at 1.5 -4, so it will be at 1.54. So simply sketch it this way. So this will be the curve of y equals the absolute value of f of x.